Hi everyone, this is Miss Moore and today we are learning about energy conversion and conservation. If you don't have a copy of the lesson template in front of you, please make your own notes today using lined paper. You will also need a calculator for today's lesson. Please pause the video here and grab a proper scientific calculator if you don't already have one. Today we're warming up with two questions. Number one, if a 2,100 kilogram car has 340,000 joules of energy, how fast is it going? And number two, where does the energy come from to power this car? Please pause the video here while you do the warm-up questions. Okay, let's go over our solutions together. Please don't forget that when you're solving a physics problem, you need to itemize the quantities given to you in the question, as well as identifying what you're supposed to find using the symbol for that quantity. Based on this being a question involving an object in motion, we're going to be using the kinetic energy formula, EK equals 1/2 times mass times speed squared. Please show all of the steps in your algebra when you're isolating v, or the speed, and I got 18 meters per second as my final answer. If you're having trouble getting 18, it may be because you forgot to bracket your numerator. When you're putting this into your calculator, you need to go 2 times 340,000 before you divide by 2,100. You also need to make sure that the entire thing is under your square root symbol so that you don't accidentally take the square root of the numerator and then divide your answer by 2,100. The second question asked us, where does the energy come from to power this car? And you may have come up with two different answers for this depending on the type of vehicle. We could have a car with an internal combustion engine, which runs on gasoline or diesel, or we could have an electric vehicle, which is battery powered. Interestingly enough, no matter what type of car you have, they rely on the same form of energy, chemical potential energy. This is the type of energy stored within the hydrocarbons that make up gasoline or diesel and is converted when these substances are burned. Likewise, inside a battery, chemical potential energy is converted into electrical energy. In today's lesson, we're going to be looking at the mathematics behind how one form of energy is converted to another. Energy is routinely transformed from one form to another in a process called energy conversion. Let's look at some examples that involve energy conversion. What energy conversions occur when a skydiver jumps out of an airplane? Well, imagine an airplane far above the ground. For somebody to hop out of that airplane and fall towards the ground, what types of energy are being converted? At first, up here, when they jump out of the aircraft, there's a whole lot of gravitational potential energy. And as they fall towards the ground, they're picking up speed. So by the time they get here, they have both gravitational potential energy and kinetic energy. As you fall, there's also a lot of friction. So all that gravitational potential energy that you started with is ultimately converted into kinetic energy and thermal energy. This energy comes from the friction between the air and your skin and clothes as you're falling. Next, please try examples 2, 3, and 4 on your own, clearly identifying each form of energy involved in the conversion. Pause the video here while you do these questions. Okay, let's compare our answers. When you turn on a lamp, you supply it with electricity. That electrical energy goes on to do work by producing electromagnetic energy, i.e. light, and thermal energy, or heat. Depending on whether it's a regular lamp, it might produce visible light, or if it's an infrared lamp, it might produce infrared rays. Thermal energy or heat is usually an accidental byproduct, something that we don't intend, unless it's a heat lamp, for example. When we turn on our cell phones, we're activating the battery, which is a source of chemical potential energy. Inside the battery, this is converted into electrical energy to power all of the device functions, such as lighting up the screen, electromagnetic energy, or producing heat, thermal energy. Again, this is usually accidental, but I'm sure you've noticed that your cell phone gets really warm after it's been on for a long time, especially if it's running energy intensive processes like a whole bunch of apps at once. And finally, when you light a match, what you're actually doing is breaking open all of the chemicals that are stored in solid form on the match tip here. When you rub that match on a surface, that thermal energy arising from the friction between the match and the surface activates those chemicals, which burst into flame, producing visible light and heat. This time, thermal energy is produced on purpose. In our next example, I'd like you to consider a flashlight, a solar calculator, and a wind-up toy, and complete this table to identify the energy conversions that allow each of these objects to serve its function. To do this, you'll have to identify the source of energy, the form of energy that's produced, and any intermediary forms of energy that are involved in between. Before we start, let's just confirm how a wind-up toy actually works. I bet many of you have played with these as children but never taken them apart to see what's actually going on inside. This will be important for identifying the energy conversions involved in this toy. Let's take a quick look at this video by Jared Owen on YouTube.
If you want one of these toy cars to move forward, you can either push it, you could build a track and use gravity to move the car forward, or my personal favorite are the cars with a pullback mechanism. No batteries required, just firmly press down, pull back the car to wind it up. Now release it and watch it go. Let's take a look at how this works. Take the case off the car and we're left with the chassis, 4 wheels, and a motor. The front wheels spin freely. There's nothing special about them. The motor is only connected to the back wheels. Now if you wind it up, you can see some of the gears moving. Let's open this up to see what's going on. There's 5 gears here, and right behind the biggest gear is a twisted piece of metal. It's called a torsion spring. The more you twist this, the tighter it gets and the more energy it stores. Once released, it will quickly unwind if allowed to do so. This spring fits quite snug inside the circular hole. If I pull it out, then the spring immediately expands, and it's not so easy to put back in, so be warned if you try this on your own toy car. On the large gear, there's some curved extensions sticking out the side. These fit right around the center of the spring. As the gear turns, the spring does too. When the car is pulled back, there's a chain reaction of gears turning. This is called a gear train, and it's what causes the spring to wind up. Let's take a step back for a moment and talk about gear ratios. I have 2 gears here of different sizes. If the big gear turns once, the small gear will turn around more than once. Now imagine the small gear had another larger gear attached to it. We could repeat this again with another smaller gear here. Turn the first gear just a little, and the last gear turns a lot. This concept is used in the mechanism for a pullback car. Now let's take a look at the car gears. There's one attached to the axle and there's one right next to it. These always move together whether the car moves forward or backwards. We've seen the large gear. Now these 2 gears have a mind of their own. This one helps winding up the car, and this one helps unwind the spring and push the car forward. The wind-up gear can slide up and down to engage or disengage with the teeth on the large gear. On the side, there's a diagonal slot that makes this sliding possible. When we start pulling back the car, the wind-up gear engages with the large gear. When the car is released and starts moving forward, the gears move the other way, which disengages the wind-up gear so it's no longer in contact with the large gear. Now during this time, the wind-down gear is doing the exact opposite. The car is pulled back, the wind-down gear is disengaged from the large gear. You can see it doing a little dance while it tries to stay out of the way. When the car is released, the wind-down gear slides into place just as the wind-up gear slides out of place. The torsion spring is causing the large gear to spin, which then moves the gears, which then turns the wheels on the car. This is where the gear ratios come into place. The largest gear moves only a little, and the back wheels of the car turn a lot. This is part of why the car can travel so far on its own. When the spring has released all of its energy, the car keeps going on its own momentum. The large gear will stop, and the wind down gear will disengage again. This time, both of these gears are out of place. This way, the car continues to move forward with minimal interference from the large gear. Imagine if the car abruptly stopped when this happened. It wouldn't be a very fun toy.
Okay, let's compare our answers. A flashlight relies on chemical energy stored in the battery to produce electromagnetic energy, i.e., light, and thermal energy a little bit by accident. We don't intend our flashlights to get so hot. A solar calculator uses electromagnetic or light energy from the sun and converts it into electrical energy to power all the computing functions and show the display on the screen. And our wind up toy uses kinetic energy from the winding action to produce more kinetic energy in the movement of the toy. So, is there in between forms of energy going on here? For our flashlight, there is. The battery converts the chemical energy into electrical energy, which is then able to produce the light energy. Likewise, our solar calculator uses the solar energy to charge its battery, which converts chemical energy into electrical energy to power the device. And finally, our wind-up toy stores elastic potential energy inside in the torsion spring, as you saw in the video, which can then be released and converted back into kinetic energy as the toy moves. As you've seen in the lessons so far, energy can be easily converted from one form to another, and when this happens, the total amount of energy remains unchanged. Even though many energy conversions are happening. This is the law of conservation of energy, which states that energy cannot be created or destroyed. Energy can, however, be transformed from one form to another, and one of the most common conversions that happens on our planet is the conversion between potential energy and kinetic energy. Let's explore this mathematically. If we ignore friction, which as we've seen leads to a lot of unnecessary energy loss in the form of heat, we can assume that the mechanical energy of a system does not change. Recall that the mechanical energy is the sum of all the potential energy and the kinetic energy stored in that object or system. So if there's no change in overall mechanical energy, then the initial mechanical energy is equal to the final mechanical energy. We have a formula that we use to express this, and it looks like this. Initial kinetic energy plus initial potential energy equals final kinetic energy plus final potential energy. The little I stands for initial, which means at the beginning. The little f stands for final, which means at the end. I'm going to put a star next to this formula because it's very important. In Physics 10, one of the problems that we're going to explore quite a bit is energy conversion involved with falling objects. A really good example of this is seagulls, because they rely on energy conversion to get their food. They collect oysters from the ocean, but they can't get through the tough shells with their beaks. So instead, these seagulls do work on the oysters by lifting them far above the ground. This increases the oyster's gravitational potential energy. When the seagull drops the oyster, all the GPE is converted into kinetic energy. If the seagull lets go right here, that oyster is going to fall quickly towards the sharp rocks down below, gaining kinetic energy as it falls. Right before it hits the rocks, the oyster has converted all of the gravitational potential energy it had at the beginning to kinetic energy. and it smashes open on the rocks. Let's explore this scenario mathematically. A seagull carries a 1.5 kilogram oyster a vertical distance of 35.4 meters above the ground. Above some sharp rocks on the beach, the seagull releases the oyster from rest. What does that mean from rest? Well, it means that the speed is zero. How fast is the oyster traveling right before it hits the ground? That means we're looking for speed, v. Now you'll notice that we have two v's going on here. We have the initial and the final speed of the oyster. So we abbreviate this with the subscripts I for initial and f for final. These are part of the variable. It's not v times I, it's just vi, or initial speed. To solve this problem, we start by writing down the conservation of energy formula. Initial kinetic plus potential energy equals final kinetic plus potential energy. Now we ask ourselves, which of these quantities must be zero based on the initial and the final time frame of the problem? Well, initially, the seagull has brought the oyster high up into the air, and it's not moving yet, so the initial speed is zero, and the seagull is about to drop it. This is what's happening initially. And then as the oyster falls, it gains kinetic energy, and right before it hits the rocks, it pretty much has zero height above the ground anymore. So we can say that the height is zero. Recall that our kinetic energy depends on the speed, and the potential energy depends on the height above the ground. So which of these quantities must be zero? Initially, the oyster has no speed, so the kinetic energy must be zero. However, the oyster has a lot of potential energy at the beginning because it's far above the ground. At the end of the oyster's fall, it has no gravitational potential energy anymore because it's about to hit the ground. So EP final is zero. The oyster, however, is going very quickly, so it does have kinetic energy right before it hits the ground. Our modified formula for this problem will therefore be initial potential energy equals final kinetic energy. Once we've got that, it's time to substitute in formulas for each of these quantities. Our formula for potential energy is mass times gravitational acceleration times initial height, or HI, which I'm going to use to distinguish between final height, which is zero. Our kinetic energy formula is 1/2 times mass times speed squared, which I'm going to further confirm is our final speed, Vf, not the initial speed, which was zero. Now it's time for some algebra. We need to algebraically isolate the quantity that we're supposed to find. We're looking for the final speed, Vf, so we have to get that by itself. We're going to systematically get rid of all of the things preventing Vf from being by itself. Let's start by multiplying each side of the equation by 2. This will undo the 1/2 on the Vf side of the equation. Now we have 2 times the mass times gravitational acceleration times initial height equals mass times V final squared. Next, let's divide each side of the equation by mass, m. This will cancel out on the Vf side of the equation. Now we have 2ghi equals V squared, because the mass also canceled out on the other side of the equation. Finally, we need to square root each side to undo the square on our V final. We're left with The square root of 2 times g times h initial equals V final. Now we can put in our numbers. V final equals the square root of 2 times 9.81 meters per second squared times 35.4 meters above the ground. When you put this into your calculator, you should get 26.3 meters per second. In example 6, a massive rock is dropped from the top of a 14.5-meter tall building. This question is very similar to the one we just did with the seagull and the oyster, so please pause the video here while you work this one out for yourself. Just like with the seagull and the oyster question, this rock is being dropped from a great height. The initial kinetic energy of the rock is zero because it's dropped. Dropped means that you just let go without adding any initial speed. You're not throwing it downwards or tossing it off, you're just letting go. Right before it hits the ground, it has no more potential energy because the height above the ground is zero. This is usually the point where students start asking, how many steps do I need to show at a bare minimum given that I understand the algebra? I've shown you here in this problem the bare minimum of algebra you must show when you're solving this problem. You have to show the law of conservation of energy. You have to show the simplification, which will look different for every type of problem that you do. We've only done one type so far. And you have to show the substitution of the related formulas. Then you need to systematically show each step in the isolation of the variable of interest, in this case, V final. And finally, you show the substitution of values. So this rock was going 16.9 meters per second before it hit the ground. Now example 7 is a little different because even though we have an object falling from a height, we're presented with different information and we're asked to find something new. How tall is the cliff that the boulder falls off of? If you feel confident, go ahead and try this question on your own. You know you got the answer right if you got 17 meters as the cliff height. If not, we're going to solve it together right now so that you can get more practice with the algebra and seeing how the algebra looks different when we have a problem of a different context. In a landslide, a massive boulder falls off the edge of a very high cliff. If the rock is traveling at 18 meters per second right before it hits the ground, how tall is the cliff? We know the speed right before it hits the ground is 18 meters per second, so that's V final. Just like in the last problem, we don't know the mass of the boulder, but we don't need the mass because it will algebraically cancel itself out when we start working out the problem. We are supposed to find the height of the cliff. So let's call that H, or H initial, assuming that when the boulder falls off the cliff, it hits the ground below. So as part of our initial condition, the height of the boulder above the ground is HI. If the boulder falls off the edge of the cliff, we can assume that the initial speed was zero. Let's start by writing out the law of conservation of energy. Kinetic energy plus potential energy initially must be equal to kinetic energy plus potential energy at the end. Which of these quantities is zero? Just like before, if the boulder was assumed to not be moving before it fell off the edge of the cliff, the kinetic energy is zero. And if the boulder is assumed to hit the ground at the end of the problem with a great speed, the potential energy must be zero when it reaches the ground. So we're left with initial potential energy equals final kinetic energy. Let's substitute our formulas for each. EPI is calculated as mass times gravitational acceleration times initial height, and EKF is calculated as 1/2 times mass times final speed. Squared. We are looking for the initial height, which will give us the height of the cliff. In order to isolate HI, we will divide each side of the equation by mass times gravity. This will cancel out the m and the g on the same side as hi. It'll also cancel out the m on the other side of the equation. So we're left with h initial equals 1/2 times v final squared all over g. Let's put our numbers in now. H initial equals 1/2 times 18 meters per second squared, all divided by 9.81 meters per second squared. This looks a little messy, so I'm going to move it over. Sorry, I know I'm cheating. You guys don't have the same power on your notes. Go ahead and pop that into your calculator, and you should get 17 meters, which is the height of the cliff. Okay, please go ahead and start assignment 3, and don't forget to check your solutions before handing in your work. Bye for now.